part of the BocaPhysics mini course on nuclear physics. In today's lecture, I'm going to continue the discussion of radioactivity. In particular, I'll discuss alpha, beta, and gamma decays. In the previous lecture on the exponential decay law, I briefly described what each of these processes entails. In alpha decay, an alpha particle is emitted, and alpha particle is basically just a helium-4 nucleus. In beta decay, an electron or a positron is emitted. A positron is the antiparticle counterpart of the electron, has the same mass, but opposite charge. In gamma decay, a photon is emitted from an excited, from a nucleus in an excited state, and that photon can have energies up to 10 megaelectron volts. Now, the theory of alpha decay does become quite involved, so I'm actually going to defer that more in-depth discussion to its own separate lecture. And today we'll just focus on what happens in alpha decay and when are those processes energetically possible. So before I begin, let's take a look back at this great chart.
Nearly all known nuclides are plotted on this chart. Stable nuclides are represented by black squares, and unstable nuclides are represented by colored squares. For lighter species, stable nuclides have roughly the same number of protons and neutrons. As the number of nucleons increases, stable nuclides are neutron-rich. Whereas beta decay occurs for at least one isotope of almost every element from hydrogen up to the heaviest known elements, alpha decay occurs for only heavy elements. For example, neodymium-144, which has 60 protons.
Okay, so what happens in alpha decay? Nucleus has Z protons and neutrons. It's unstable and it emits an alpha particle. And a daughter nucleus. So the total number of nucleons is conserved. So altogether, initially started out with Z plus N nucleons, and as I said before, an alpha particle is basically just a helium-4 nucleus, which means it's got 2 protons and 2 neutrons. So therefore, the daughter nucleus the next question is, does this always occur? Does any kind of unstable nucleus decay into an alpha particle plus something else, plus a daughter? And the answer is no. The next question, of course, is, well, when does such a decay occur? When can it occur? So you want to look at the energy, specifically the kinetic energy released in this process. So the kinetic energy released is going to be equal to the difference is in mass of the parent nucleus and the sum of the mass of the helium nucleus and the mass of the daughter nucleus. Okay. So what I'm going to do is I'm going to add and subtract Z and E to this expression. And the reason I'm doing this is because I need to rewrite this expression in terms of the atomic masses. You see in nuclear data tables, it's the atomic masses that are given, not the nuclear masses. So if I add ZME to the nuclear mass, that'll give me the atomic mass. So therefore, this is mass, atomic mass of the parent atom, minus. And here we can see we can break this into two parts. We can write this as 2Me here, and maybe better write it below there, Z minus 2Me, okay? So again, just adding and subtracting Z times the mass of the electron, and then furthermore breaking that apart up over here into 2 and Z minus 2, okay? So therefore we wind up with minus mass of the helium-4 atom plus mass, atomic mass of the daughter atom, okay? So in order for alpha decay to be possible, it must be the case that the kinetic energy is positive, and therefore that's the same thing as saying is that the mass of the parent atom is greater than the sum of the mass of the helium atom, helium-4 atom, and the mass of the daughter atom, Z minus, having a number of protons Z minus 2 and number of neutrons N minus 2. So let's take an example. Let's take U-235. And I just want to verify that in fact it does decay and can decay via the process of emitting an alpha particle. So its daughter nucleus is going to have 4 fewer nucleons, which means the total number of nucleons is now going to be 231. And it will have 2 fewer protons, and that is the element thorium. So I want to compare this mass with the sum of these two masses. Mass of U-235 is 235.043930 atomic mass units. Now the mass of helium-4 atom is 4.002603 atomic mass units. And the mass of thorium-231 is 231.036304 atomic mass units. So these two together have total mass 235.038904 atomic mass units. So this sum is less than this one. So this process is energetically possible. We've confirmed that. And I'm going to calculate how much kinetic energy is released. And we need to multiply this by a conversion factor. One atomic mass unit is equal to 931.5 megaelectron volts over c squared. Therefore, this c squared will cancel with this one, and this u will cancel with the units of the masses. And when I plug everything in, I will wind up with an answer of 4.68 megaelectron volts is going to be released in this particular decay. Okay? Let me just leave that up there for a minute. And let's look at one more example. Let's consider the potential alpha decay of strontium-90. So let's put a question mark behind this. Does this process occur? Well, what you want to do is consult a nuclear data table and look at the mass of strontium-90. And again, write down the mass of the helium-4 atom, which is 4.002603 U, and the mass of krypton-86, which is 4.002603. What you'll see is that the sum of the mass of the helium atom and the mass of the krypton-86 atom is equal to 89.913214 atomic mass units. So clearly, the mass of the potential parent nucleus, strontium-90, is less than the sum of the mass of the helium atom and the sum of the krypton-86 atom. So this does not occur. Okay? So if alpha decay is energetically possible, that means that the mass of the parent atom has to be greater than the mass of the helium atom plus mass of the daughter atom. Okay? So uranium-235, in fact, does decay via this process. Strontium-90 absolutely does not. Now, before we leave the discussion of alpha decay for the present lecture, I want to make a comment about the half-lives. Half-life of U-235 is extremely long. It's 704 million years. Another unstable nucleus that decays via the alpha decay process is polonium-212. Both of these do occur, and if you're interested, you can check out the energetics of this. Polonium-212 will emit an alpha particle, and also a daughter nucleus will be lead-208. The strange thing here is, in comparison to these two, is that this has a half-life on the order of 0.3 microseconds, a little bit less than that actually. So the strange thing here is that the half-life of U-235 is so very long, 704 million years, and the half-life of another heavy species, polonium-212, is so very short, it's 0.3 microseconds. And the question is, why is it so? Any theory of alpha decay has to explain or give, at the very least, give insight into why these half-lives are so different from species to species. Okay? Let's next turn our attention to beta decay. Beta decay means you're talking about three different kinds of processes potentially. Electron emission, positron emission, or electron capture. I'm going to go over all three of these, but I'm going to begin with the emission of an electron. And this is beta minus decay. Parent nucleus has Z protons and neutrons, and it emits an electron and a daughter nucleus will be produced. Now remember, the number of nucleons is conserved, and furthermore, an electron is emitted. So that means that the daughter nucleus is going to have one more proton and one fewer neutron. And I'm just going to add space here at the end because there's actually a third particle that's produced in beta decay, but I'm going to get to that in a minute, but for now I'm just going to concentrate on these, the parent and then also just the two of the products of this decay. Now, let's look at a particular set of isobars. Whenever you have beta decay occurring, the parent nucleus and daughter nucleus are isobars of each other. That means they have the same total number of nucleons. So let's look at the A equals 12.
The A equals 12 isobars are lithium-12, beryllium-12, boron-12, carbon-12, nitrogen-12, and oxygen-12. Notice that each of these isobars has a different mass, with carbon-12 having the smallest mass. Carbon-12 is the only stable member of this group. Beryllium-12, boron-12, and nitrogen-12 all have half-lives on the order of milliseconds. Lithium-12 has a half-life on the order of nanoseconds, and oxygen-12 has a half-life that is but a tiny fraction of a second.
I'll ask the same question as I did when we were talking about alpha decay. Do all nuclei undergo the process of beta decay? And the answer is no. What are the conditions or condition that for beta decay to occur? Just as before, it's got to be the case that the amount of kinetic energy released has to be positive. So therefore, the mass of the parent nucleus minus mass of the electron plus mass of the daughter nucleus is going to be positive quantity. So this has to be greater than this. And just as before, I rewrote the expression in terms of the atomic masses because, again, nuclear data tables list the atomic masses, they don't list nuclear masses. So let me just rewrite this expression. I'm going to go ahead add Z times mass of the electron and subtract Z times mass of the electron. So if I look at these first two terms, that's just going to be the mass of an atom, atomic mass of an atom that has the Z protons and N neutrons. And down here, you can see that you've got Z plus 1 times mass of the electron. So the second term just becomes minus mass of atom Z plus 1 N minus 1 times C squared. So that's the kinetic energy released in beta decay. So in order for beta decay to occur, it must be the case that the mass of the atom, the parent atom, has to be greater than the mass of the daughter atom. Now remember, two nuclei that are in this in beta decay are isobars of each other. Let's go back and look at that graph of the 8 equals 12 isobars.
Let's focus attention on the isobars to the left of carbon-12. Lithium-12 emits an electron and decays into beryllium-12. Beryllium-12 emits an electron and decays into boron-12. And finally, boron-12 emits an electron and decays into the stable nuclide carbon-12.
Okay, so let's start at the very left-hand side with lithium-12. And I'll write down the number of protons and neutrons there as well. That decays into beryllium-12. And plus an electron and plus that third particle that I will be getting to. Beryllium-12 decays into boron-12 and boron-12 decays into carbon-12. Now carbon-12 is a stable nuclide. You can see that from looking at the diagram that it actually makes sense because it sits at the very bottom of the plot. Any of its other isobaric neighbors have energy, or rather have rest masses greater than that of carbon-12. Okay, so carbon-12 is stable. So let's go ahead and calculate how much energy is released in this final decay here. And of course, mass of carbon-12 is precisely 12 atomic mass units. And we multiply by a conversion factor. You see that 13.4 megaelectron volts of kinetic energy is released in this particular reaction. Okay? Now I'm going to finally get to the mystery particle here. there was a very troubling discovery, and that was when people were observing the amount of energy released, the electrons did not all have 13.4 megaelectron volts. Remember, if we just assume that there are two products of this particular decay, because the electron is so much lighter than the carbon nucleus or any kind of nucleus in beta decay, you would assume that most of the kinetic energy, or actually nearly all of the kinetic energy, would be carried away by the electron, okay? However, it was observed that the electron didn't just have energies that were very close to 13.4 megaelectron volts. There were electrons observed to have energies in this whole range, just above 0 megaelectron volts, all the way up to nearly 13.4 megaelectron volts. So, what does this mean? Conservation of energy appeared to be in jeopardy. As you do the calculation, there seems to be a certain amount of kinetic energy available, but yet, where does it go? And it fell to a Swiss physicist by the name of Wolfgang Pauli, who proposed the existence of another particle. Let me rewrite it here. So we've got Zn goes to Z plus 1 and minus 1 plus an electron plus this third particle. And this third particle had some rather interesting properties. And in fact, it was Enrico Fermi who christened this particle the neutrino. So if there were an additional particle that was a product of this kind of decay, well, then that would explain why the energies observed by that the electrons were observed to have not all just have the same value, they can have a range of values. So the properties of the neutrino are that it's very light, negligibly small mass, or zero mass, and furthermore, does not carry electric charge. And very weak interaction with other matter. And for some time, people did not believe that there was such a thing as a neutrino. Thought, well, gee, it's just some kind of a clever bookkeeping device to preserve the conservation of energy. Well, it wasn't until the 1950s where the American physicist Cohen and Raines actually came up with experimental evidence of the existence of the neutrino. And without getting into the details of it, essentially they placed a large tank of water next to a nuclear reactor. Now in the nuclear reactor, a lot of beta decays were produced, and consequently, a lot of these neutrinos were also produced. And what they calculated is that these neutrinos would interact with the large tank of water only very weakly, and that they observed something like only 3 events taking place by all these, I think something like in the order of 10 to 20 potential neutrinos per hour. Only 3 interactions were believed, were calculated to take place inside the tank of water. Now, one further thing I want to clarify this a little bit. In this actual decay, it's an antineutrino, not a neutrino. There is a difference between the two, and if you're interested in learning more about that, I urge you to look at the BocaPhysics particle physics lectures, where we do discuss antineutrinos versus neutrinos. And there's also a further refinement. I'm going to put a subscript E there, and that indicates that we're talking about an electron antineutrino, because there are different types of neutrinos. There are electron neutrinos, muon neutrinos, and tau neutrinos as well. But what we're interested in is antineutrino, and oftentimes authors we'll leave off the bar and we'll E because for our purposes in nuclear physics, that is really not an important point. So that is the process of beta decay. In order for beta decay to occur, the mass of the parent atom has to be greater than the mass of the daughter atom, and we just calculate the amount of kinetic energy released by this process, and it was because of experimental observations regarding the electron that led to the proposal of the neutrino and actually the anti-neutrino. Okay? So let me just leave this up here for a minute, and we'll move on to a different kind of beta decay. We'll look on what does an unstable nucleus emit a positron. So let's go back to that plot of the A equals 12 isobars. And this time we're going to look at the right-hand side of the graph.
Let's now focus attention on the isobars to the right of carbon-12. Oxygen-12 emits a proton, and the daughter nucleus is not an A equals 12 isobar, rather it's nitrogen-11. Let's move to nitrogen-12, which does emit a positron, and the daughter nucleus is once again the stable nuclide carbon-12.
Okay, the decay we were looking at is that of nitrogen into carbon-12 by emitting a positron and a neutrino. This time it's a neutrino, it's not an anti-neutrino. The general form of beta plus decay looks like this. So this is the parent, as Z protons and neutrons, decays into a daughter nucleus, one fewer proton and one more neutron. Plus the positron plus the neutrino. So the same questions that I asked before, I'm going to ask again. Does this decay occur for every unstable nuclide, every unstable species? The answer is no. What condition has to be satisfied in order for this decay to occur? So once again, we want to look at the kinetic energy released in this decay. And once again, I'm going to rewrite this expression in terms of the atomic mass. So first add Z times mass of the electron and subtract Z times mass of the electron. And once again, I'm not giving myself enough room. There is a C squared at the right-hand side. So I'll just read this off. This is mass of nucleus, Zn, plus Z times mass of the electron minus, brackets, mass of the daughter nucleus, Z minus 1, N plus 1, plus mass of the electron plus Z and E. So all we're doing is adding Z and E, Z mass of the electron, and subtracting it off. These first two terms combine to give you the mass of the parent atom. this becomes, we're going to rewrite this a little bit. We have mass of electron plus mass of electron plus z minus 1 mass of electron, okay? And so this z minus 1 times mass of the electron combines with the nuclear mass term, and then I'm going to be left over with 2 times mass of the electron. And that's how you calculate the amount of kinetic energy released. Therefore, the condition for this process to occur is for the kinetic energy to be positive. In other words, the mass of the parent nucleus has to be greater than the mass of the daughter nucleus plus 2 times mass of the electron. I'm going to go ahead and calculate the kinetic energy released in this decay. This is the atomic mass of nitrogen 12 minus mass of carbon 12 plus 2 times mass of the electrons. So I'm going to plug in numbers. The mass of nitrogen 12 is 12.018611 atomic mass units, and mass of carbon 12 is just 12 plus 2 times times 0.000548580 all times c squared, and I left it out here, but these are also in atomic mass units as well. And last but not least, you also want to multiply by a conversion factor, and I'll stick this down here. (931.5 mega electron volts over c squared, all over 1u. So the 1 over u will take care of these u's due to the masses, and that c squared in the denominator will cancel with the c squared in the numerator. So this becomes together 16.3 mega electron volts released in this particular decay. Okay? So again, the condition for beta decay to occur is that the mass of the parent nucleus has to be greater than the mass of the daughter nucleus, which has 1 less proton, 1 more neutron, plus 2 times mass of the electron. Okay? Now let's go ahead and look at the very basic, simplest kinds of beta minus decay and beta plus decay for comparison. Very simplest kind of beta decay, beta minus decay, would be that of a neutron that decays into a proton and an electron and, of course, an antineutrino. Neutrons are unstable outside of a nucleus. fact, the neutron has a mean lifetime of about 880 seconds. And yes, I did say that when you do nuclear physics, people quote lifetimes, usually half-lives rather than mean lives. The neutron, I just prefer to quote the mean life, and that's 880 seconds. So that's unstable outside of the nucleus. So how much energy is released here? Well, kinetic energy release is equal to mass of the neutron minus mass of the proton plus mass of the electron. So basically it's just Mn minus Mp minus Mp all times c squared. So I'll just read this off. And you know, I left out there are U's here as well. All the masses are in atomic mass units. So mass of the neutron is 1.008665. Mass of the proton is 1.007276. And finally, the mass of the electron is 0.00548580. And that's all times c squared. And we have to multiply by the conversion factor. So that'll get rid of the atomic mass units and write this in terms of mega electron volts over c squared, and of course that 1 over c squared cancels with this one. Doing the math, we will wind up with .783 mega electron volts. So neutrons are unstable outside the nucleus, and when this decay occurs, 0.783 mega electron volts of energy is released. Okay? So what's the beta plus counterpart of this process? Well, that would be a proton decaying into a neutron plus a positron plus a neutrino. Does that occur? The answer is no. The reason why is you just look at the relative masses. This is the mass of a proton and this is the mass of a neutron. There's no way there's enough mass for this basically kind of inverse process to take place. So in fact, protons are stable and do not decay. And for that matter, so are electrons. Okay. So those are the two simplest possibilities for beta decay, beta minus and beta plus. The neutron decay absolutely occurs. Corresponding proton decay does not occur. Can't occur because no kinetic energy would be released in this process. You'd have to, energy would have to be provided. Okay? So let's look at the very last of these three processes, electron capture. In the case of electron capture, parent nucleus captures an electron, and that results in a daughter nucleus with one less proton and one more neutron, and of course neutrinos also emitted as well. So once again, Does this always occur? No. When does it occur? Well, that's if kinetic energy is released. If kinetic energy is positive in this process. So let's go ahead and do the math once more. Kinetic energy released is equal to the mass of the parent nucleus, mass of the electron, minus mass of the daughter nucleus, which has one less proton, one more neutron. We do the same thing as I did before. I'm going to go ahead and add ZME, Z times mass of the electron, and I'm going to subtract it off. So I'm just adding and subtracting it. In that way, these first two terms add up to mass of the atom, atomic mass of the parent nucleus, minus, now over here, I'm going to group this mass of electron with this term, so this basically becomes minus Z minus 1 and E, so I'm going to add this and this, so it's minus, altogether Z minus 1 times NE, so then I can combine that with the daughter nucleus, so this gives me the atomic nucleus, the atomic mass of the daughter. And all times C squared. So again, for this kinetic energy to be released, in order for this process to occur, mass of the parent must be greater than the mass of the daughter, and that should be a +1 down here. Okay? So again, parent captures an electron, daughter is produced with one less proton, one more neutron, and a neutrino is emitted in that. And here we add and subtract my ZME, Z times mass of the electron. So those two terms combine up to the mass of the parent atom, and then I'm going to combine this term with this term, and add all those together. It just gives you the mass. So these two together becomes mass of the daughter atom. I want to look at a problem, basically the possible decays of U-231. So I'm going to see if any of these kinds of processes can occur, and let's do the math here. So before I do that, I'm going to go ahead and write down the conditions for it to occur and how much kinetic energy will be released. So beta minus decay Let me read this off. For beta minus decay, the mass of the parent atom has to be greater than the mass of the daughter atom, which has one more proton and one less neutron. Kinetic energy release is the difference in those two masses times c squared. For beta plus decay, so when a positron is emitted, the mass of the parent atom has to be greater than the mass of the daughter atom plus 2 times the mass of the electron. And kinetic energy released is the difference between the parent atom and the sum of the daughter atom plus 2 times mass of an electron. And finally, for electron capture, mass of the parent atom has to be greater than the mass of the daughter atom, and the kinetic energy release is just the difference in those two masses times c squared. So let's apply all three of these to U-231. Beta minus up here. If beta minus decay occurs, that means that we'll decay into neptunium, 231. Put a question mark behind that. So we just need to consult tables of our table of nuclear data. Mass U-231 is 231.036, 293 atomic mass units, and the mass of neptunium, 231. Is 231.038245 atomic mass units. Clearly, right away I can say no, because the mass of the daughter would be greater than the mass of the parent, so this is not possible. How about beta plus decay? And such a decay would be U-231 decaying into protactinium 231 plus positron plus neutrino. So compare these two, once again, the answer is no. Mass of uranium is less than the sum of mass of protactinium, which is 231.03584 atomic mass units, plus 2 times 0.000548580 atomic mass units. You add those up, you wind up with 231.036981 atomic mass units. So reason why you've got so many decimal places should be obvious by now. Okay, electron capture. Is this possible? Can this occur? And if we just compare the mass of U-231 with the mass of protactinium was like, which I just have written right here, well, the answer is yes, that can occur. So electron capture is energetically possible, and it does occur. And if we want to figure out how much kinetic energy is released, well, it'll just be those mass differences, 231.036, 293, minus 231.035884, all atomic mass units, and of course multiplied by the conversion factor. And give me an answer, 0.381 of energy will be released in this process. Okay. Now, one final question is, does alpha decay occur? And why don't we see if that's possible in this case? So alpha decay would be U-231 emitting an alpha particle plus thorium-227. Okay, so if I compare the sum of the two masses, mass of the helium-4 atom and mass of the 227, thorium-227 atom, you can see clearly that's smaller in mass of the uranium atom. So therefore, alpha decay can occur. So it is possible for one of the beta decays to occur and one of the alpha decays to occur for the same species. Now, alpha decay is a lot less likely. The probability of this occurring is much smaller than for electron capture. So sometimes when you look at the heavier nuclides, that you'll see a branching can occur there. Okay, so just leave this up here for a minute. And last topic we need to cover in today's lecture is gamma decay. Gamma decay, nucleus is in an excited state and it emits a photon, and in so doing it returns to the ground state. As I mentioned, gamma rays can have energies up to 10 megaelectron volts. So let's take it for instance. Let's suppose that we have, let's see what we've got. Lead 208, and it's an excited state, and it emits a gamma ray with energy 2.62 megaelectron volts. So what happens to what else happens, I should say, to the nucleus that did the emitting? Well, go back to relativity and just consider the so-called Pythagorean relation. E squared is equal to momentum times speed of light, quantity squared, plus mass times c squared, all squared. So we've been using this an awful lot here. For a massless particle, however, E is simply, energy is just simply equal to momentum times the speed of light. So if the gamma ray has energy 2.62 megaelectron volts, it has momentum 2.62 megaelectron volts over C. And therefore, by conservation of momentum, the nucleus has to have the same magnitude of momentum, but opposite direction. So the recoil momentum of the nucleus is also going to be 2.62. megaelectron volts over C. And I might also want to figure out, well, what's the recoil energy? Of the nucleus. Well, that's just equal to p squared over 2m, momentum squared over 2m. So let me just write this out. Which is 2.62 megaelectron volts over C. I'm going to pull the c squared down into the denominator. And this is the mass of the recoiling nucleus, the mass of lead 208. The mass of the nucleus is 207.976652 atomic mass units. And we need to multiply by a conversion factor. And yes, we do have an additional c squared down there. So once again, the c squared cancels with this one, the should cancel with this one. You'll be left with 1 megaelectron volt in the denominator to cancel out 1 in the numerator. So we do the math. We're left with 7.7 electron volts. So that's the recoil energy of the nucleus. And that concludes alpha, beta, and gamma. Now, I don't want you to leave you with the impression that we've covered absolutely everything. We've covered the groundwork, but there are such processes as isomeric transitions. There's delayed proton emission, delayed neutron emission. There's spontaneous fission, and so forth. So we just covered the basics in this class, and if you go on to take a upper level course on nuclear physics, you certainly get into a discussion of those topics.